Here we have a problem P, which we want to solve. P is too big to be solved right away, so therefore we divide it into two subproblems, P1 and P2. The solutions to P1 and P2 are combined to a solution to the original problem, P. It may even be the case that we need to subdivide P1 and P2 into their own subproblems. So this is a well-known idea. It is top-down programming by stepwise refinement. It may also be called divide and conquer, or perhaps better, divide and combine, because we divide a problem into two subproblems and we combine the solution of P1 and P2 to a solution to our original problem. In some cases, it is possible to split P into a subproblem P1 of the same shape and nature as P. And the solution to P is obtained by combining the solution of P1 with a simple calculation, symbolized here with this shape. When it comes to the solution of P1, the pattern recurs. So we see that a solution to P1 is obtained by combining a solution to P2 with a simple calculation. P2 is of the same shape and nature as P1, and this pattern repeats itself until the problem is reduced to a small problem, which is easy to solve. So the last one here, Pn, is so small that we can solve it right away without additional dividing into subproblems. This drawing is actually too complicated to really grasp. It is sufficient to understand this drawing, namely that we divide P into a subproblem P1 of the same shape and nature as P, and we combine the solution to P1 in a simple way to obtain a solution to P. This is the fundamental idea of recursion. The solution to P recurs at a smaller scale, and we are able to combine the solution to P1 in a simple way in order to obtain a solution to P. In some situations, it may be more appropriate to divide the problem P into two problems P1 and P2, each of the same shape and nature as P. And this pattern recurs at more detailed levels until we reach some subproblems which can be solved immediately. So this may be called tree-shaped recursion, whereas the first example we saw is more like a linear recursion. Now let us study some practical examples of recursion. I organize my scheme programming in two panes. At the top I have my scheme buffer with a scheme function which I transfer to my reader-val print loop at the bottom. And it may be done in different ways, but here I select my function and I evaluate the current form. The function is called number interval, and let us call it number interval from 1 to 10, and this gives me the list of numbers from 1 to 10. And the way it is implemented is that I distinguish between two cases. In the first case, the first parameter f is smaller than t, and in that case I recur because I identify a subproblem which is one smaller than the original problem. So the number interval from 1 to 10 is obtained by calculating the number interval from 2 to 10 and counting this result together with 1. In case that the subproblem is small enough, that is, f is large enough, f becomes t. In that case, the subproblem is easy to solve because it is just the empty list. So we have it here. Number interval calls itself recursively, and the result of the recursive call is combined with cons to the result of the original problem number interval. Eventually, the subproblem becomes so small that instead of calling number interval recursively, the result of the inner recursive call is the empty list, which is combined and combined and combined by means of cons to the result of the outer problem. As another example, we have string merge, which takes two lists of strings. I define it, and we can play with it. String merge. The first list may be 1, 2, 3, and the other list may be abe, cat. So we merge these two lists of strings to a single string and get this result. So up here we see that string merge is divided into 3 cases in a conditional, and the last case is the recursive case, where the function calls itself here on 2 lists, which becomes 1 element shorter than the original list. Of course, this is only possible if both lists are non-empty, and this is guaranteed by this conditional. In case one of the string lists become empty, we use an easy fix, namely applying string append on the remaining strings in the list. I will not go into details with this. In case you wish, it can be programmed in a more simple and perhaps a slightly more complex way. We leave it as an exercise. Let us take a look at a final example called string of char list ? It is a predicate that determines if a text string is composed exclusively by characters in the char list. Before we proceed, let us define the function and the helping function, and let's try it out on an example. So is the string abe composed by the characters A, B, and D? No, it is not, so we get false. But if we try out the variant here, we get true. The function immediately calls a helping function which introduces a parameter of integer type I, which proceeds through the characters of the string. It becomes 1 larger for each recursive call. So again, as always, there are 2 cases. There's a recursive case, and there is the terminating case. And the terminating case is here when I has traversed all the characters in the list. Assuming that we have got a positive result, then the result at the very end is true. In the recursive case, for a given I, we assure that character number I is member of our character list, and that the rest of the list, as identified by the increased number I, is composed by characters in my character list.